In this video, we will walk through hyperparameter optimization on the Hopsworks platform using MNIST example, a Jupyter notebook, and we're going to in fact use two approaches to hyperparameter optimization. One will be synchronous and the other will be asynchronous. So first we'll log in with the default password, admin, and you'll notice that I've already run a tour, the deep learning tour, over here, and it created this project called Demo Deep Learning. So I'm going to go straight into the Demo Deep Learning project. And what we can see here is that unfortunately I've only got one GPU to play with. So that means I won't be able to do hyperparameter optimization in parallel. If I had 10 GPUs, 20 GPUs, 100 GPUs, that would make the training go much faster. But unfortunately I don't. On different platforms, so if we look at a different platform here, we can see we can have 22 GPUs and this will go much faster. But in this example, I'm going to stick with the one GPU. So let's just go back. Okay, so I'm going to start the Jupyter notebook, and that's up here in the top left hand corner. We click on the Jupyter button, and there we go. And we can see that there's different options for starting the Jupyter notebook. This time we're going to select the parallel experiments option, and we only have one GPU, so the number of GPUs per executor will be 1, and the number of parallel experiments, or the number of executors, will be 1 as well. And we're okay with the 4 GB for the executor and 2 GB for the driver. So let's go ahead and start this Jupyter notebook server. And I'm going to start with synchronous hyperparameter optimization. I'm going to go to the parallel experiments example. Let's click on that. And I'm going to go to TensorFlow. And from in here, I'm going to do two different examples. The first one will be grid search, and then the second one I will do asynchronous hyperparameter optimization with random search. So let's start with grid search. And I'm going to start with the fashion MNIST, grid search fashion MNIST example. So this will be in your demo tour. I'm just going to go straight away and run this example. It takes quite a while to run. Fashion MNIST is actually a more challenging data set than MNIST, classical MNIST, which is the handwritten digits. Fashion MNIST is in fact 10 different types of clothing items and shoes as well. And it was developed by Zalando, a company. And in this example, we have a function called wrapper, and we have two different hyperparameters, the learning rate and the dropout rate. And you can see that the hyperparameters are supplied as parameters to our training function. And the training function itself, in this example, it's TensorFlow, not Keras. It has quite a lot more code in it. Because the function wrapper is going to be quite large, we've actually factored it into, you can have nested functions in Python, so we can see there's a function inside this function, and that's completely fine. The training data is local in the cluster on HDFS. We're not downloading it from the internet. And if we go further down, it's using TF records, and what we can see down here is it's also using TensorBoard. So we can see we've got our TensorBoard here, and it's using the estimator API. So we'll go down further. We can see that the Spark application has started running, and let's go down here. So the next cell after our training cell is this particular cell, and this cell defines a dict containing two different hyperparameters. So the first hyperparameter is the learning rate, and there's 3 different values for that learning rate supplied, and there's 2 different values for dropout supplied. Now what that means is that there's going to be 6 experiments, because it's going to be the cross product or combination of all of the learning rates and dropout rates we supplied. That's what grid search does. And the first trial or experiment will have the learning rate of 0.001 and a dropout rate of 0.45, and the last experiment will have 0.0001 and the dropout rate of 70%. So these experiments will run from the top to the bottom. And you can see now that this piece of code is running. In this example, it's not Maggy, so we're not going to get feedback in terms of printouts directly in our notebook. But this one is slightly different in that if we go through it, we can see that we're calling grid search, experiment.grid search. This is the name of our function, the wrapper function. These are our hyperparameters. And then we have to tell it whether this particular example is either maximizing or minimizing. We're trying to maximize accuracy, so we say the direction is max. The only other thing that's kind of slightly of note here is that we have this version resource notebook. So that notebook is defined on the previous line, and that notebook is basically saying, what it's saying is that we want to store a copy of the notebook that ran this experiment. So then you can go back and repeat this experiment again later on. So it will be stored in our datasets directory in the experiment, the application folder for the experiment. So let's go back to Hopsworks at this point, and we'll open our user interface. We can notice that the GPU is busy down here in the bottom left-hand corner. And what we can also notice is that there's a TensorBoard option appeared here. So this TensorBoard is for the one executor that's running right now with the GPU. If we had 10, we would have a drop-down list with 10 different TensorBoards that we could look at. We only have one. So we can click on it, and it will show us how training is progressing for that particular executor. Remember, we're going to have 6 of these running, so this is only one of 6. And we can see that, you know, the accuracy is increasing. It's getting better, but eventually it'll run out of number of steps to train for, and that trial will complete. Now, in this particular example, it takes quite a while to run because we have 6 of these trials to run, and each one takes a minute or so to run. So what I'm going to do is I'm going to actually stop the training. So I'm going to stop this application, and I can go back to our notebook and shut that down as well. You can just click on close that and close that. And what I'm going to show you is the experiment that just ran, but also one that I ran earlier, so we can see what would happen if we waited for all 6 of the hyperparameter trials to complete. So this one, I just killed it, so we can see it says killed. But if we go back to one I ran earlier, it's this one. And it succeeded. It was grid search. I can copy the application ID, paste it up here to see the TensorBoard for that particular run. Now what happens is that each of the executors will run on a different container with the GPU, and they'll aggregate all of their TensorBoard logs into the file system, the same file system. And TensorBoard is now visualizing these application logs from that file system. So what we can see here is that the best experiments are at the top. So I think the best one here looks like it's 80% accuracy, so 80.39% accuracy, with a higher learning rate of 0.001 and a medium dropout rate of 0.45. So if we let this run for longer, it's possible that the lower learning rates would get better, but for this example, that's the result we have. So that's synchronous hyperparameter optimization, because each one of these trials ran as a separate task in Spark. And if we look at the asynchronous approach that we support in the platform, I can use the same setup that we have. I can use the same Jupyter notebook. We just shut down. So we can see that it's not running. Oh, we do have one running. So let's shut that down. And now what we're going to do is we're going to go back to parallel experiments, and we're going to run asynchronous hyperparameter optimization using the Maggy framework. So this is a handwritten MNIST example, the one that we had before, but it looks slightly different in Maggy. So let's go through this example. So we have our function, our training function here, and we have 1, 2, 3 hyperparameters. And the fourth parameter here is called reporter, and that's going to be used to report metrics. So how's the accuracy or loss progressing from this executor here back to the driver. And the driver has a hyperparameter optimizer that will decide, should I continue with this trial or should I early stop it? And that's what asynchronous hyperparameter optimization is about. Basically, making sure that trials that aren't performing good get stopped early so that you free up resources to be used by other GPUs, because GPUs are a precious resource. So I just started the training function running, which will start the Spark notebook. So what we can see here is that we have slightly less hyperparameters, and if we go down, we slightly less hyperparameters defined within the function. They're defined instead at the as parameters to the function. What we can see in this example that's slightly different is that in our driver we now have something called a search space. And this search space is the hyperparameters that you want to use. In this case, we have kernel, pool, and dropout. Dropout is a double, whereas pool and kernel values are integers. And we've defined a range for the kernel size from 2 to 8, and a range for the pool size from 2 to 8. And for the dropout rate, we've defined a range from 0.01 to 0.99. So this particular optimizer is going to use random search. It's going to pick random values in these ranges and run a trial. In total, there will be 15 trials. We're going to try and maximize accuracy. There's a heartbeat interval. After 5 seconds, the executor will report its metrics back, and then we have early stopping interval and early stopping minimal values. So let's start this running and see what happens. And what will happen is we have 15 trials and we only have one executor. So unfortunately, it's going to run them serially, one after another. So that basically means that we have to wait for each of them to run. Ones that perform poorly. So the early stopping rule in this particular case, if you read earlier on in the notebook, it says the median stopping rule. So it's a very simple strategy. If the performance of a trial falls below the median of other trials at similar point in time, we're going to early stop that trial. So what we can see here is that Maggy knows that there's 15 experiments and we've done, or 15 trials, we've already done 4 of them. But we can see that the best performing trial currently is at 96% accuracy. So in the first video of this series, where we just trained with a set of static hyperparameters, we didn't get quite as good accuracy. We're already getting slightly better accuracy now. We can also see that the logs that are printed out here, they include a 0 at the beginning. That's the executor ID. If you have lots of executors, there will be a different ID printed out here for each line, for each executor, because they're running in parallel in the cluster. And if we actually go and look at how the printing works, we can see that we have some print functions here. What we're doing, in fact, is overriding the print function to send those the contents of those print statements back to the driver, where they're printed out in the notebook, and also here. And if we go down here, we can see those results being printed out here. So now this particular example has completed. We can see that there were 15 trials. The best combination was a kernel size of 8, a pool size of 4, and a dropout rate of 35%. And it gave us 96.85% accuracy. So that completes this video on hyperparameter optimization using both synchronous and asynchronous approaches on the Hopsworks framework.